Topic 4.6, which is about the electromagnetic effect. We started this topic the last session. What is electromagnetism or electromagnetic induction? What is electromagnetic induction? Electromagnetic induction states that the change in the magnetic field produces EMF. And how we can change a magnetic field either by moving the wire which is placed in a magnetic field, or either moving the magnet. So by changing a magnetic field anyway, like either moving a wire or a magnet, whenever there is a change in magnetic field, there is always an induced EMF or current. So in this example, say we have a wire which is placed between the two magnetic poles. When we move this wire either up or down, so in this example we are moving down, but we can also move up. So if we move this wire, there will be a change in the magnetic field, and due to the change in magnetic field, what will happen? There will be an induced current. So we will see galvanometer, the needle will deflect. When the galvanometer needle deflect, it shows that there is a current produced due to a change in magnetic field. And this EMF will last once there is, like if we keep on changing, then EMF will induce. But if we stop changing the magnetic field, example, we move this wire and then stop. So the moment we stop, now there is no change in the magnetic field. As a result, when there is no change in the magnetic field, what will happen? This wire will not, there is no induced current. So the needle of the galvanometer or a zero center galvanometer will return to the center. So whenever there is a change in magnetic field, there is a current. If there is no change in magnetic field, there is no current. How we can find the direction of the induced current? So we can use Fleming's right-hand rule. So Fleming's right-hand rule is used to find the direction of induced current. So first finger, the index finger pointing towards the magnetic field south of a magnetic field, or from north to south. Second, the thumb represents the movement of the wire, and the finger will turn in a direction or shows the direction of induced current. So as you can see, the first one, in the first example, on the left-hand side, this one. So what will be the direction of induced current? How to identify the direction of induced current? My index finger should point towards the south. So south is on the right-hand side. So my index finger is pointing towards the south. The wire is going down, so my thumb should point down. So my index finger is pointing towards the south and my thumb is pointing down. Where my finger is pointing outwards or towards me. So as a result, when we are moving this wire downward, there will be an induced current which will come outward. And for the second figure, on the right hand side, what will be the direction of induced current? So first finger, index finger pointing towards the south, so that is towards the right hand side. The thumb is pointing up. The wire is, we are moving the wire up, so thumb is pointing up. Where the second finger is pointing, that is the direction of the current. So second finger is pointing into or towards the screen. That's why the direction of induced current will be into the screen. So this will be the direction of induced current. So using a right-hand rule, Fleming's right-hand rule or a right-hand rule, we can identify the direction of induced current. So we will use Fleming's right-hand rule to identify the direction of induced current. The factors on which this induced EMF depends or the current depends, that is how fast we are moving. If we are moving the wire faster, or if we are moving the magnet faster, there will be more induced current. If we are using a stronger magnet, there will be more induced current. And if we are using a longer wire or using several turns or looping the wire, that will also increase the direction of the amount of induced current. So these three factors affect the deflection, not the direction of a deflection, but amount of deflection. If we use a stronger magnet, there is more current, so the galvanometer reading will deflect more. If we move the wire faster, there will be a greater change in the magnetic field and direction of there will be more deflection. And if we use more turns, greater the length of a wire in a magnetic field, greater the induced EMF. So in this state, three factors which affect the size of a deflection. We did discussion yesterday. Just quickly, I will go through. So we use, it depends on the strength of a magnetic field. It depends on the speed of the wire, movement of the wire, at what speed we are moving the wire. And the third factor depends on the length of the wire in a magnetic field. So if we have greater length of a wire in a magnetic field, that will have greater induced EMF. Now the second part, which explain the direction of a deflection in a magnetic field, that is a Lenz's law. What is the Lenz's law? Lenz's law is used to determine the direction of induced current. What Lenz's law state? Lenz's law state an induced current always in a direction to oppose the change in magnetic field. What does it mean? If I simplify this statement, example, we have a solenoid, a wire is turned around, and we have a permanent magnet, north and south. According to the Lenz's law used to identify the direction of the induced current, and it states that induced current will always produce in a direction to oppose the change in the magnetic field. Example, if I'm moving the magnet towards the coil, what happened to strength of a magnetic field? Will it increase or decrease? If I move the magnet closer towards the coil, what happened to the strength of a magnetic field? If I'm moving the magnet, like magnet is placed here, but now what I'm doing, I'm moving the magnet more towards the coil or solenoid. So when we are moving the magnet more towards the solenoid, what happened to the magnetic field or strength of a magnetic field? It gets stronger. That's true. First thing, when we are moving the magnet, there is change in the magnetic field which produce EMF. That is first thing. But the second thing, what happened, according to Lenz's law, what is the meaning of a law? Means practically always it is giving the same result. That is why it is a law. So second thing, what happened, when we move the magnet towards the coil or a solenoid, the strength of a magnetic field will increase. So according to Lenz's law, what the solenoid will try to do, solenoid will try to oppose the change in magnetic field. So how a solenoid can try to oppose this, how solenoid will try to stop this magnet moving towards, so which whenever the current produced in a solenoid in this example, so how it can oppose it by, it can oppose by repelling. Then how a solenoid can repel? So when there's a current in the solenoid, current will produce in a direction so that north pole will be on the left hand side and south pole is on the right hand side. Why it happened? According to Lenz's law, when the current start to flow in the wire due to a change in magnetic field, that current will always try to oppose or try to stop the magnet from either moving towards or away. So what happened? When we are moving the magnet towards the solenoid, there is a change in the magnetic field, and that change in a magnetic field induces EMF. So there is a current here in a solenoid. which direction the current produce. Current will always produce in a direction, try to oppose the change. So how it can oppose the change, how it can stop the change? So if you are moving the magnet towards, the magnetic field is increasing. So a solenoid will produce a current in a direction so that north pole will be on the left hand side and the south pole on the right hand side. So how we can identify the direction of the current? In this case, we will use a right hand rule. So if the current is going in this manner, the right hand grip rule. So if the current flow in this manner, on the left hand side will be the north pole and on the right hand side will be a south pole. But if the same figure, if we were having a same figure, but now we are moving the magnet away. So if we move the magnet away, the same thing happen. What solenoid will try to do? It will try to oppose. And how it can oppose the change in the magnetic field? Say we have a permanent magnet. So we have north and south, and this time we are moving the permanent magnet away from the solenoid. For example, this is a solenoid and we have a zero center voltmeter or a galvanometer. So now what is happening in this figure, as we are moving the magnet away, here what was happening, the strength was increasing. The strength of a magnetic field was increasing. And this solenoid will try to oppose. And here, when we are moving the magnet away, what happened to the strength of a magnetic field? The strength of a magnetic field will decrease. And what solenoid will try to do? Solenoid will try to oppose this. How a solenoid can oppose this? If a strength is decreasing, so what solenoid will try to do? It will try to attract. So as a strength of a magnetic field, will decrease. So what solenoid will do? Solenoid will try to oppose. And how a solenoid can try to oppose this? This time, what pole will be produced here? Because the magnetic field is decreasing, it will try to increase. So this time, south pole will be on the left hand side and the north pole is on the right hand side. If north pole is on the right hand side and south pole is on the left hand side, how we can identify the direction of a current? Remember the right hand grip rule, that if my north pole is on my right hand side, my fingers turn in the direction of a current. So my fingers will rotate in a direction of a current that is pointing downward. So what will be the direction of current in this example? So the direction of the current will be like this. So both ways, when we are moving the magnet towards, the strength of a magnetic field was increasing, a solenoid will try to decrease it, try to oppose. When magnet was moved away, magnetic field was decreasing, solenoid will try to increase. So it will always try to oppose the change in magnetic field. So example, if in this example, when we were moving the magnet towards, if the needle of a galvanometer or a voltmeter deflected towards the right hand side, if we are moving it away, the needle will deflect towards the left hand side, because the direction of the current produced when the magnet is moving towards and the magnet is moving away, that is opposite of each other. So Lenz's law simply state that whenever there is a change in a magnetic field, it produces the e.m.f, it produces the current, but the direction of the current always try to oppose the change in magnetic field. So 4 different examples for like 4 different possibilities are there, because maybe we are moving a magnet towards and away, or north pole is facing or south pole is facing. So 4 different possibilities are there. Now, for example, I'm moving the magnet towards the solenoid. So what happened to the strength of a magnetic field? As a magnet is moving towards, so strength of a magnetic field will increase because they are closer to each other. As a result, when the strength will increase, what this solenoid will try to do, it will try to oppose. And how a solenoid can oppose? By producing a same pole. So what pole will be here? The solenoid will have a current, and that current produces a magnetic field, and that magnetic field is always try to oppose the change. So solenoid is always try to oppose. So if the magnetic field is increasing, it will try to decrease. If magnetic field is decreasing, it will try to increase. So north pole is on the left hand side and south pole will be on the right hand side. Then how we can identify the direction of the current? So to identify the direction of the current, remember we did right hand grip rule, that my thumb should always point towards the north pole and my fingers turn in the direction of the current. So thumb is pointing towards the north pole and the fingers turn in the direction of the current. So where current, as I grip the wire, like example, this is a wire, north pole is on the left hand side. So my thumb is pointing towards the left. As I try to grip, so which direction current will start to flow? The current will, you can use a chat or a mic to state the answer. So which direction current start to flow in the wire? The current start to flow upward. Because we are looking at this phase. Same way, if we are moving the magnet away, the north pole is there facing the solenoid and that north pole is moving away. So what happened to the strength of a magnetic field? The strength of a magnetic field will start to decrease. What solenoid will do, what is the characteristic of a solenoid, is always try to oppose, always try to resist the change. So what solenoid will try to do, it will try to resist the change. So if the magnetic field is decreasing, solenoid will try to attract the magnet, like magnet should come closer to solenoid. So how it can attract the magnet? By producing an opposite pole. So south pole will be on the right hand side and north pole will be on the left hand side. And when I apply the rule here, when we apply the rule, if my thumb should point towards the north, so in this example, north is on my right hand side. So thumb is pointing, the fingers are pointing downward. When I catch the wire in the direction of the current, or I know the magnetic field, so current will go downward. So in this example, the current will be down. So what will be the difference in the two readings? Because the direction of the current is opposite. If the direction of the current is opposite, example, if the needle was deflected towards the right, in this one, the needle will deflect towards left. And same way, the third example, south pole is facing. And if south pole is facing and I'm moving the magnet towards, if I'm moving the magnet towards, what happened? Again, the strength of a magnetic field will try to increase. What solenoid will try to do? It will try to oppose. So what pole should be there on the left hand side? How it can oppose? You can use a mic or a chat to state the answer. What pole should be there on this side, on the left hand side, to oppose it? If I'm moving a south pole of a magnet towards the solenoid, a solenoid will try to oppose the change. So what pole should be there? That's right. So it should be south pole on the left hand side and north pole on the right hand side. And now what is the direction of the current? How to identify the direction of the current? So we'll again use the right hand grip rule. Thumb is pointing towards the north and my fingers turn in the direction of the current. So automatically my fingers will point downward. As you can see, when I apply the rule, my thumb is pointing on the right hand side. And when I grip the wire, my fingers at the last, it is going downward. So the direction of the induced current will be downward. And if the direction example is downward and current is moving in this manner, so the example, the needle is deflected towards the left hand side. And if we are moving the magnet, the same magnet, we are moving it away. So what happened to the strength of a magnetic field? The strength of a magnetic field will decrease. What this wire or a coil will try to do, it will try to oppose. It will always try to oppose. So it will try to stop or it will try to oppose. Because the strength is decreasing, it will try to attract, it will try to increase. So what pole will be induced? North will be induced here on the left hand side, and south will be induced on the right hand side. And the direction of the current, when you apply the rule, the direction of a current using a right hand grip rule will be upward. So this is how the needle will, so as you can see, the direction of the current is changed. So the direction of a deflection will also change. So the deflection, the direction of induced current or direction of the deflection depends on two factors. Number one, which direction we are moving the magnet. And number two, which pole is facing the solenoid. So these are the two factors which will affect the direction in which the current is induced in the solenoid. Number one, direction in which we are moving the magnet and which pole is facing. So if we are moving a north pole, then magnetic field increase, it will try to decrease by opposite pole. If we are moving it away, north pole is moving away, so the magnetic field is decreasing, it will try to attract, so south pole will be here. If we are moving a south pole towards, so opposite, because strength of a magnetic field is increasing, it will try to decrease. And if we are moving a south pole away, so strength of a magnetic field will start to decrease, so it will try to increase. So the idea is that whenever there is a change in magnetic field, there is always a current. The current produces a magnetic field which always try to oppose the movement of the magnet or the change in magnetic field. So as you can see, if I'm moving a magnet north pole towards a solenoid, so north pole will be on the left hand side and south pole is on the right hand side. And we can use a right hand grip rule if we want to find the direction of the current, thumb pointing towards the north and our fingers will turn in the direction of current. And in example 2, if we are moving a north pole away, so what will happen? Because the magnetic field start to decrease, so this will try to increase by appearing in opposite pole. And how to find the direction of a current? The thumb will point in the direction of a north and our fingers will turn in a direction of current. So using a right hand grip rule, we can identify what will be the direction of the current due to a change in magnetic field. So suggest 3 possible changes to the system that would increase the direction of induce. So we can use a stronger magnet, or we can increase more turns, or we can move it faster or increase the speed of the magnet. Now I want participation from everyone, so try to answer different parts. These questions are now related to all about electromagnetic induction. So describe an experiment used to produce a current in a solenoid. So same figure is there. This we did yesterday, so I'm quickly going through it. That a solenoid and a magnet you will draw, and how this can work by changing a magnetic field. It will induce EMF. So example, if I say, can you mark a north pole? Use a screen annotation. Mark a north pole on this. Which side will be the north pole of the solenoid? Use the screen annotation to mark the north pole on the solenoid. Yeah, that's right. So on the left hand side, we'll have a north pole, and opposite south pole will be there. And if I say direction of the current in this part of a wire, what will be the direction of the current if north pole is pointing on the left hand side? That's right. So the direction of the current will be upward. That's correct. Yeah, that is right. These are the questions related to electromagnetic induction. Can be demonstrated using a solenoid. In a space below, draw a label diagram of operators to demonstrate electromagnetic induction. So how we can demonstrate? We can have a solenoid, we can have a zero center voltmeter or a galvanometer, and a permanent magnet. All should be labeled. State one way of using operators to produce induced current. By how we can just moving the magnet, or we can also say moving the solenoid. Explain why your method produce induced current. Because when we move the magnet, there is a change in the magnetic field. And whenever there is a change in magnetic field, that's why there is a induced current. Without changing the operator state, what must be done to induce a current in opposite direction as original? Like I want to change the direction of the current. So what I should do? What we can do if we want to change the direction of the current? So example, if first we were moving the magnet towards, then what we should do, because the direction of the induced current depends on two things. Either change the pole, either we can change the pole, or we can change the direction of a motion of magnet. So we can change the pole facing the solenoid. Or what else can be done? Or move the magnet in opposite direction as the original. So that will produce a current in opposite direction. And then we need a large induced current. If we want to increase the amount of current, what we should do to increase the amount of current, we should move the magnet. A large induced current is there. So without changing apparatus. So when they say without changing apparatus, you cannot use a stronger magnet here. Because to use a stronger magnet, we have to change the apparatus. So large induced current, move the magnet faster. Which create or which produce greater change in magnetic field. And that will produce a large current. So in this question, name the process that cause a potential difference due to a movement of a nearby magnet. So this is called electromagnetic induction. Then the second part, as we are moving the magnet towards, so what pole will be there north and what pole will be there south, and the direction of induced current will be in this manner. The magnet is pushed into a solenoid and then it brought to rest. So describe the movement of the pointer. So the needle will deflect first. Why it will deflect? Because there is a change in magnetic field, and then it will return to zero. Why it return to zero or return to center? Because as I mentioned here, first the magnet is pushed and then it stops, brought to rest. So first when magnet was moving, there was a change in magnetic field. Once the magnet stopped, there is no change in a magnetic field. So there is no induced EMF. The next part, the magnet is now pulled out. So we are moving out the magnet. Compare the pointer. So what we will see and at a higher speed. So we'll see a large deflection in opposite direction. Why there is a large deflection in opposite direction? Because the direction of the pole which is produced here will be opposite if we are moving the magnet away. So the pole which is induced here will be south and pole north here, and the direction of induced current will also change. So if the need, and it is moving it faster, so there will be a greater change in the magnetic field. That's why there will be a large deflection. And due to the change in direction of the motion of a magnet, so direction of the deflection of needle will be opposite.